The FREEDAM Research Consortium involved the Department of Civil Engineering of Salerno University acting as coordinator, the Department Argenco of the University of Liège guided by Professor Jean-Pierre Jaspart, the Department of Civil Engineering of the University of Coimbra guided by Professor Luis Simoes da Silva, the Department of Structures of the University of Naples Federico II guided by Professor Raffaele Landolfo, and two industrial partners, FIP Industriale in Italy and Ofelitz Metallomeccanica in Portugal. The FREEDAM project was aimed at the development of beam-to-column joints equipped with friction dampers. In particular, two configurations have been developed, whose difference is due to the orientation of the friction damper concerning the beam bottom flange. In both cases, the top flange of the beam is fixed using a bolted T-stab. Therefore, the center of rotation is located at the level of the T-stab stem close to the column flange. This is aimed to prevent damage to the deck slab. In the first configuration, namely horizontal configuration, the friction damper is connected to the beam bottom flange by a bolted haunch. The friction damper is parallel to the beam bottom flange. In the second configuration, namely vertical configuration, the friction damper includes the haunch bolted to the beam bottom flange. The friction damper is aligned with the plane of the beam web. FREEDAM is the acronym of Free from Damage Steel Connections. Because of the use of the friction dampers, FREEDAM connections can dissipate the earthquake input energy almost without any yielding. It means that even in the case of destructive seismic events, structural damage to connections is negligible. The bending resistance of the joint is governed by the friction resistance of the damper and by the lever arm that is increased due to the haunches. The beam-to-column joints can withstand any desired value of the rotation demand under seismic events by simply designing the length of the slotted holes of the friction damper, thus governing their stroke.
FREEDAM dampers are constituted by steel plate elements which are assembled by S-train bolts. Slotted holes are used to allow the axial displacement of the device. The slip resistance depends on the amount of bolt preloading and on the value of the friction coefficient, which depends on the coating process adopted for the contact surfaces. The coating process has primary importance to assure an adequate value of the friction coefficient and to assure the stability of the cyclic response of the damper. In particular, the coating has to guarantee a friction coefficient as great as possible because the connection slippage and the surface loading condition has to be prevented. Besides, the coating material has to be selected to reduce the wearing of the contact surfaces under cyclic loads, which is the cause of the loss of bolt preloading and, as a consequence, of strength degradation under cyclic actions. Furthermore, the adopted material has to prevent stick and slip phenomena. During the development of FREEDAM dampers, about 15 different contact surfaces have been investigated and the best coating procedure has been identified. After the preliminary tests, 3 different coating materials have been selected. Successively, 130 tests under cyclic loading conditions have been performed. Both low-velocity tests and high-velocity tests, performed at FIP Industriale, have been carried out. Besides, cyclic loading histories simulating the random nature of the earthquake loading have been carried out. The information gained from these tests allow the choice of the best coating material and coating technology. This is the main reason why the mark FREEDAM is now a recorded mark.
Long-term tests have been performed at the University of Liège under service loading conditions on shear bolted connection with preloaded bolts. This means on connections which are quite similar to the ones characterizing the FREEDAM damper assembly. So during 6 months, the evolution of the bolt preloading has been measured, and therefore the loss of preloading with the time. These results are of primary importance so as to define at the end the best assembly procedure which allows to reduce as much as possible the losses of preloading in bolts. The final objective is to prevent any slip in the connection, but also to ensure their rigid behavior under service loading conditions and during the whole life of the structure.
Even though the FREEDAM damper is essentially subjected to axial forces, the displacement field is not so simple in actual beam-to-column joints, like the one occurring when the FREEDAM damper alone is tested. Experimental tests on beam-to-column joints have been performed to check the behavior of the friction damper when introduced into conceived structural detail for FREEDAM beam-to-column joints. This is also the main reason why two different structural details have been conceived. In particular, the quality of the shape of the hysteresis loops is affected by the structural detail of the connection. Experimental tests on external beam-to-column joints have been carried out at the University of Salerno, while experimental tests on internal beam-to-column joints have been performed at the University of Coimbra.
It is well known that the main difference between external joints and internal joints relates to the behavior of the web panel in shear. And in internal joints, there is an increased shear action that is properly taken into account. What was observed in the tests and proved in our tests is that they are adequately taken into account, and so they behave well. These hysteresis loops that were observed in the tests in Coimbra are exactly matching those that were recorded in the Salerno tests. So again, proving that there is a very good, stable behavior of the FREEDAM connections.
The finite element analysis on FREEDAM connection were carried out to investigate the local behavior of the beam-to-column joints equipped with the FREEDAM dampers, in order to evaluate the effect on the force transfer mechanism from the dampers to both beam and column. The analysis shows also the differences in terms of local response between the two types of FREEDAM dampers, namely the on-shed device with horizontal sliding and the rib device with vertical sliding. The adopted modeling assumption effectively simulates both the global and the local response of the tested joint, as it can be observed comparing the experimental and simulated response curve and the corresponding deformation pattern. In the experimental campaign, no damage was observed in the steel elements. However, the numerical analysis showed the distribution of small plastic deformation in the connection that are not evident from the back analysis of experimental results. Plastic deformation can be also observed in bolts of the dampers. Indeed, the horizontal dampers configuration produce a shear-type bending effect in the shanks, with two bearing contact in all bolts of the device. On the contrary, the bolts in the vertical dampers have one bearing zone at mid-length of the clamping shank, which leads to larger local plastic strain. In addition, in this second case, the bolts close to the column face don't show any plastic strains.
The transfer mechanism of shear force was investigated in order to characterize any aspect related to the design of T-stab and L-stab connection and column face, because this element should guarantee the resistance due to combined tensile and shear forces to avoid perimeter failure. In particular, finite element analysis allows evaluating the magnitude of the shear force transferred by each component of the joint that cannot be measured experimentally. Indeed, L-stabs transfer greater shear force compared to T-stab connection. Joints with hinged dampers are characterized by levels of maximum shear force transferred by the T element of about 50% of the total shear force, while the L-stab reach values close to 100% the total applied shear force. The joints with reed damper exhibit the same behavior, with shear transferred by the L-stabs reaching values almost 2 times greater than the total shear force for rotation values close to 0.06 radian. In addition to the preloading force MB adopted in the test, a value 50% smaller and a value 50% greater than NB were also considered. It should be noted that in all cases 1.5 NB is smaller than Eurocode 3 recommended preloaded force. As expected, the variation of bending moment is proportional with bolt pretension, although differently under sagging and hogging moments. This difference is strictly related to the joint configuration, but it does not vary with beam depth, the clamping force, or the friction coefficient. The stiffness of the joint is not affected by the variation of clamping force, since it is determined by the stiffness of the other component of the joints, namely the connection at column face and column wet panel. Parametric finite element simulations were also carried out to investigate the influence of different sides and shapes of the connected members. The flexural response of the joints equipped with proposed dampers is not symmetric. On average, the auger resistance is about 25% greater than the sagging one, at core rotation equal to 0.04 radians. This behavior is mainly due to the higher deformability of the L-stabs in tension, which leads to a loss of preload higher in the bolts of the damper. In addition, the evolution of the equivalent viscous damping per cycle at different levels of rotation is rather high for all cases with average value equal to 0.35 at 0.04 radians.
The design for robustness is a request coming from modern codes and standards, including the Eurocode. If reference is made to Eurocode 0, it is stated that the structure should be designed in order to avoid damage initiated by events such like impact, explosion, or consequences of human errors to an extent disproportionate to the original cause. And this request is made for any structures designed according to the Eurocode. And so, in other words, the objective is to ensure the structural integrity when a structure is subjected to an exceptional event. The exceptional event is an event with a very low probability of occurrence, but which can induce significant consequences. And so the objective is to avoid the development of a progressive collapse in the structures, and so to save life, but also to secure the intervention of the safety services in case of exceptional event. To achieve this objective, the Eurocode is proposing different strategies. Design strategies for identified threats, such like impact, explosion, but also strategies for unidentified threats, aiming at limiting the propagation of a local damage, and so whatever is the initiating cause. The design for robustness have been included in the development process of the FREEDAM joint solution by considering 2 scenarios. Impact, which can induce dynamic effect, but also the loss of a column in a structure. Two universities have been involved in this investigation, the University of Coimbra and the University of Liège. And for that, they have used two different kinds of approach, experimental and sophisticated numerical studies. In particular, the FREEDAM joints have been investigated in isolation when subjected to an impact, but also structures equipped with the FREEDAM joint solution have been investigated when subjected to a column loss scenario. The final aim of all this investigation was to highlight the added value of using the FREEDAM joint solution, which exhibit a quite significant deformation capacity, as it is well known that ductility, and in particular the deformation capacity, play a key role in a structure subjected to an exceptional event.
The behavior of the joints and their high loading rate is not completely understood. However, the joints play an important role in the behavior and in the response of the structures under exceptional loading, as for example impact and the column loss. So research in this topic, in this field of research, are still important. Experimental tests on impacts at the University of Coimbra was carried out in one side FREEDAM joints and also in their components, and at the University of Liège it was carried out impact tests on double-side FREEDAM joints. Based on the results, numerical tools were validated, and based on that results, parametric studies were developed in order to evaluate the detailed response of the FREEDAM joints and also in their components. The investigation finally was focused on the different impact mass, impact speed, and also at the end under the different levels of loading energy.
Well, the impact tests have shown that we have a beneficial effect in terms of resistance, while the deformation is kept. So again, we can see that the FREEDAM joints behave well. If we want to quantify what is the exact relationship, this is not easy to establish at this moment, but we can state that we get roughly between 1.2 and 1.3 times increased resistance under impact loading when compared to quasi-static testing.
In the case of a column loss scenario, it has been demonstrated that the high level of deformation capacity of the FREEDAM joints is really an added value, as it allows the activation of significant membrane forces in the system, and so provides some robustness to the structure. Such an activation of the membrane forces really makes it possible to find a new state of equilibrium of the structure, a new state of equilibrium in a deformed shape, obviously, and in such a way that the structural integrity of the structure can be guaranteed.
The financial support of the European Commission has allowed performing an exhaustive experimental program. During the project, not only FREEDAM dampers and beam-to-column joint sub-assemblies have been tested, but also the seismic simulation of a real-scale two-story building has been performed. The pseudodynamic testing facilities of the Strength Laboratory of Salerno University have been used. The earthquake record with its accelerogram is the main input. The motion equations are numerically solved by fixing the mass matrix and the amount of structural damping, while the reaction forces due to the structure are experimentally evaluated. The lateral displacements derived by the numerical integration of the motion equations are imposed on the structure using servohydraulic actuators working under displacement control. The reaction forces due to the structure are directly provided by the load cells equipping the actuators. Therefore, the structure reactions are the real ones, In other words, there is no mathematical model of the structure, but the actual experimental response. The reactions thus evaluated are used for the integration of the motion equation. The procedure goes on step by step up to the end of the earthquake record and until the structure comes back to the rest.
Within the FREEDAM project, 2 earthquake simulations have been carried out on a real-scale 2-story steel building. The first building has been equipped with traditional connection using in particular extended end plate connection with RBS. The second building has been equipped with FREEDAM connections. Destructive seismic events have been considered, such as the record of Imperial Valley earthquake amplified to a PGA equal to 1.1 G, the Coalinga record amplified to a PGA equal to 0.8 G, and others. Even though the interstory drifts are comparable for the 2 buildings, in light of observed damages, the exhibited behaviors are completely different. The building equipped with a traditional connection was subjected to the fracture of the bottom beam flanges or the fracture of the weld in the heat-affected zone. The dissipative zones are subject to yielding in case of severe seismic events. Because of yielding, the primary structural system is subject to damage and needs to be repaired. The repairing of the yielded ends of the beam is quite difficult and cumbersome. Significant economical losses occur because of direct and indirect losses.
FREEDAM connections are free from damage connections. The dissipative zones are constituted by the friction dampers, which are specifically designed to dissipate the earthquake input energy. The connection can be designed to accommodate any rotation demand. After destructive seismic events, practically no damage occurs in the connection.